Good afternoon, ladies and gentlemen. My name is Donald Cameron. Now, let's clear a few things up at the start. I'm an Irishman. I've got a Scottish name, and I live in England. So I hope that's as confused as you're going to be during my short presentation this afternoon. My presentation is a sound solution to the problems of particulate build-up and material flow within power generation plants. So what are sonic soot blowers? Well, they are pneumatically operated horns that produce low frequency, high energy sound waves. And the sound waves are produced when compressed air enters the wave generator and forces the only moving part, the titanium diaphragm, to flex. Here is a typical sonic soot blower. The bass tone is produced when compressed air enters a wave generator and causing the titanium diaphragm to flex. That creates a bass tone, and then this bass tone is converted into a number of selected key frequencies by the size and shape of the bell section. Does the shape of the bell section matter? Well, yes, it is of vital importance to have an exponential or bell shape. On the right, you see an easier, simpler, cheaper, linear, conical design. If sound waves were to be emitted from this, they would be emitted as a parallel beam. If you have the exponential shape on the left, they are emitted in a cyclonic effect, thus giving much better coverage inside the vessel. And so what do they do? Well, sonic soot blowers are employed wherever ash, dust, powders, or granular materials are processed, generated, stored, or transported. To understand a little bit more about sonic soot blowers, first of all, we have to understand what is sound. And you may be amused or concerned to know that our ear doesn't actually hear sound. Our ear is a pressure-sensitive mechanism that detects very rapid pressure fluctuations. That is why we fly or we swim underwater, our ears go pop. They're detecting very rapid pressure fluctuations. And that is exactly what is produced by a sonic soot blower, a range of very rapid pressure fluctuations. If you look at the next diagram, you will see that in a 350 Hertz sonic soot blower, there are 350 sound pulses per second. And this creates a positive push followed by a negative, which weakens and breaks the cohesion bonds between the particles, dislodging the material. So it's a very rapid push-pull. Here's a typical sonic soot blower waveform. Sonic soot blowers, although we direct them towards a particular fundamental frequency which we want to achieve, I'll mention the main range in a moment, they also produce harmonics. Like in a piano, you play middle C, you go up an octave, you play the next highest C. So let's say the fundamental range you want to have here is at 100 Hertz. You'll also get harmonics happening at 200 Hertz, 300 Hertz, etc. With our long experience, we use the following frequencies to cover the wide range of applications. So we go from 350 Hertz through 230, 120, 75, up to 60 Hertz. So why do we have all these different frequencies? Well, high frequencies such as 350 Hertz have the same power but have shorter wavelengths and are used for high intensity, short distance material debonding. For example, if you have a silo with a hopper and the hopper is breaching, we would use a higher frequency device in there because that acoustic bar we want it used up over 1 meter, 2 meters, 3 meters. The opposite is true as well. The low frequency, for example, is 60 Hertz, has longer wavelengths and are employed for high power, long distance material debonding. Again, taking a silo as an example, if there was side material build-up, rat holding, let's say a 30,000 ton cement silo, we would install a 60 Hertz on top, and that would prevent this sidewall build-up. It's because the sound waves are very long and they will pass up and down that huge silo space. I'm going to give you a little demonstration of the power of sound waves only. We do a lot of research with the University of Liverpool on an ongoing basis. And here is a special room where we have an acoustic cleaner and a vessel and no other outside influences. And this is simply using sound waves, no vibration, no nothing else, to make that material flow. Purely sound waves. And we have accelerometers strapped on the side of the vessel to measure and prove that there is no vibration happening. A very, very powerful material debonding. One of the key areas which we are involved in is the story of the tussle between sonic soup blowers and steam soup blowers. I'm sure many of you are familiar with steam soup blowers, even if you're not familiar as yet with sonic soup blowers. So have sonic soup blowers certain advantages over steam or water soup blowers? Well, we certainly believe so. If you look at a couple of the key areas, first of all, price, operating and maintenance costs. The sonic soup blower is cheaper to purchase and install. It is considerably more economical in its use to operate, and there's virtually no maintenance costs. If you look at physical damage, corrosion and erosion, the sonic soup blower will not cause any physical damage or vibration to either tube bundles or structures. And because there's no steam or water involved, they will certainly not cause any corrosion or erosion problems. So no physical damage, I say. Well, can we prove it? Well, the reason is that we operate between 420 hertz and 60 hertz, which is way, way above the resonance frequencies of steel or concrete. You need to be down somewhere below 15 hertz to start getting into that area. Well, can we prove it? Yes, we can. Here's one example. Here we have a large silo. This case was a floor silo, concrete silo with a metal base. We installed a microphone halfway down the silo. We installed a 75 hertz unit on top. We strapped on a couple of accelerometers onto the wall of the silo and the hopper section, and we sounded the unit. And you can see, being a 75 hertz, its fundamental frequency is it's appearing at 75 hertz, and we have the harmonic at 150 hertz. So all this powerful sonic debonding is going into the material. The orange line is the vibrations picked up on the side of the silo or on the hopper. Now this could be a forklift truck driving by. It could be a rotary seal or a conveyor on the bottom of the silo. Many reasons. But you will see that none of this powerful debonding sonic waves are being absorbed into the structure whatsoever. Totally, totally safe. Other things that are interesting about sonic sound wave, they travel like 344 meters per second in air, faster through solids, and 360 degrees. So unlike steam soup blower, it's not just leading tube edge cleaning, but total tube cleaning. One other important difference between steam soup blowers and sonic soup blowers is that, is that sonic soup blowers actually prevent ash being deposited in the first place, rather than leaving it like a steam soup blower until the end of the shift when you're trying to blast a hard crust of the tubes. So by sounding a sonic soup blower typically for 5 to 10 seconds every 5 to 10 minutes, it prevents the ash from building up in the tubes. So what is required to operate a sonic soup blower? Only two things: normal compressed air, 5 to 6 bar, and it uses about 18 to 22 liters per second when sounding. But remember, it's only sounding for 5-6 seconds every 10 minutes or so. And electrical control voltage to activate the solenoid valve. This can be by a strapped-on timer, a plant PLC, or a local PLC. One of the questions we're often asked, can sonic soup blowers be easily retrofitted? Well, indeed they can. In fact, A lot of our applications are doing that. It's doing that. We can use the vacant ports left by redundant steam soot blowers, or we can use any hopper or hatch in between the tube bundles, which is ideal for us. So easy to retrofit. So let's look at a few examples. This is a large zinc refinery where we installed 6 120 hertz on an ESP. The ESP had used a mechanical wrapping system which was causing damage and causing inefficiency due to damage. The photograph on the left shows the units being installed. The photograph on the right, we supply a dedicated DLC in a waterproof cabinet, and they have eliminated their wrapping system. Here in London, there is one of the largest waste-to-energy plants in Europe, called London Waste. It has 5 large boilers where we installed our units, both 60 hertz and 75 hertz, on the economizer sections of the plant. The photograph on the left shows an external view of one of the units, and on the right, an internal view. Were they successful? Well, here are the comments of the plant manager. We have had an internal problem with our economizer mid-bank steam soot blowers for some time. The tube configuration of that bank is such that it's plain tubes at the top of the bank and thin tubes at the bottom of the bank. This arrangement makes cleaning much more difficult, and historically we would have to shut down the boiler and go into the economizer pretty soon after the development of such a fault in order to repair the steam soot blowers and manually clean the tube banks because of the rate of fouling being so high. However, currently draft losses have remained insignificant thanks to the operation of the sonic soot blowers. I would happily endorse your product. Another large power plant, this time in South Korea, where we installed 24 120 hertz sonic soot blowers on a large SCR. This SCR initially had retractable steam soot blowers. You can see on the left one of the now redundant retractable steam soot blowers. Beside that, one of the sonic soot blowers. The picture on the right, a close-up of one of the sonic soot blowers. They have an excellent testimonial of the efficiency of those units and the savings they have made in not trying to run their steam soot blowers and the high maintenance costs they suffered from trying to do that. This is a power plant in South Africa where we installed 8 75 hertz units. This plant was originally built as a gas plant, but that proved too expensive, so it was converted to heavy oil, and actually within a few weeks they had a serious problem in the superheater and economizer sections. Here is one of the units we installed. You see it's an existing hatch in between tube bundles, and that cured the problem. Closer to home in Scotland, this is a big refiner at Ineos, which is formerly BP at Grangemouth. It had 4 heavy oil boilers, and we installed 24 75 hertz in the economizer sections, which were causing them a lot of problem. So the sonic soot blowers replace rotary steam soot blowers. It's not just in power plants. One of the things we talked about today with the speakers is heat recovery. On the left, it's one of the heat recovery plants. It's a small one, but it's got 2 units in. Before this, they tried other methods, which never worked. They had a bad thermal conductivity. The only way they could clean it properly was to stop it and push the tubes out. They installed those, and that cured their problem. The one on the right, typical biomass, is another area. So all areas within power generation within the cement plant we can deal with. But cement plant is one of our biggest markets in any case, cement industry. I'll just run through a few other applications. Silos. It says there we have pure products in 50 countries, actually 60 countries now. If you look at the photograph on the left, you'll see the favoured hammer rash, which is very prevalent in plants. And we simply have installed a 350 acoustic cleaner to stop the bridging of the outlet. On the right, this is a plant in Haiti. And this guy, the plant manager, is so pleased at having installed acoustic cleaners on top of his unit, because he wrote to me and said, here's a photograph of me. I recovered 1,000 tons of cement, which I was able to sell, and my boss thinks I'm wonderful. So he's very pleased to have his photograph taken. Baghouse applications, big area for us. On the left is a small filter unit. This is a Global cement pre-packing plant. And this caused all sorts of problems, even though it's a small unit. They were getting cross-contamination, they were getting hopper pluggage. They used to send a guy in to try and clean it. One day he decided he wanted to keep the rotary seal going as he was cleaning it. He didn't do that again. The photograph on the right is a very large smelting plant filter. In fact, this here is the height of a couple of guys standing here. This is a reverse air system where they closed off one of 12 sections and reversed the air down. What happened there was they got a sudden deluge of material, blocked the hopper, shut the filter down, shut the smoking plant down. We cured that by hanging units both inside of the bags and in the hopper section. Here's another little demonstration of the power of a filter plant and the sonic soup blower inside it. This next slide I'm going to show you is in Turkey. It is a wood plant. This filter handles the fine wood dust. The plant shut down. The reverse air system purged away as it does for 30 minutes. No more material coming out of the hopper section. Filter clean? No. We put an acoustic cleaner, held it through here, opened the hopper. This is after 30 minutes of purging down. They're excited. So it not only does it stop hopper pluggage, it cleans the inside walls, it cleans the bags, it gives its filter bags extra life. We have customers who have got 50% more bag life by using this type of technology. Other applications are ID fans. A lot of ID fans in cement plants. The one on the left is in Egypt, the one on the right is in the UK. What it does, it prevents unscheduled shutdowns. You're not having the fan going off balance, the sensor tripping out, and you're having to shut the plant down. What is the cost of that? Keeps the fan balanced until you have a scheduled plant shutdown. Very simple, economical way of saving a lot of money. So those are just a few examples of not only the power industry, but other applications within the cement industry. So the Quartersonic range of sonic soup blowers are safer, they have lower purchase and installation price, they are more efficient, with lower maintenance, easy to retrofit, and fully automatic. That is the end of my little presentation this afternoon, ladies and gentlemen. I thank you for your kind attention.